In section 12.2, we looked at arithmetic sequences and series, and what that meant is that we found a rule that was either addition or subtraction. So in the pattern between the numbers, the rule was to add or subtract the same number each time, and we called that a common difference. When we look at geometric sequences and series, that means our rule, and that's for geometric, sorry, the rule is called a common ratio. That means we want to multiply or divide by the same number. So instead of adding and subtracting with the arithmetic sequence and having a common difference, our rule now is to find a common ratio or multiply the number by the same number to get to the next. So remember we talked about writing sentences recursively. That means that we needed to start with the first term, and to get to the next term, we look at the previous term, which is a sub n minus 1, and multiply that by the common ratio. All right, so common ratio, if we wanted to find that value, you can take a number and divide it by the number before it. And we're going to do that right down here. So if I look at this, I have 2 to 6 to 18 to 54 to 162. If I wanted to calculate the common ratio, I could take a number and divide it by the number before it. And you can probably look and see that from 2 to 6 you multiply and get 3, and then multiply by 3, multiply by 3. But if it's not as obvious, just take a number and divide it by the number before. So 54 divided by 18 is 3. 162 divided by 54. All of these are 3. So my common ratio is 3. So if I have a geometric sequence, I have my first term is 2. My common ratio is 3. And then remember, we can write this recursively. If I know the first term, my next term is the previous term times 3. All right, so this would be what I need to have if I'm writing the recursive rule. All right, example 2 says to show the following sequence is geometric. Now, I don't have a list of numbers that I have up here. I really just have a formula. So if I were to make a list of numbers, I'll just do 4 of them. This is my first number, second, third, and fourth. That means here n is 1, n is 2, n is 3, n is 4. So if I put these into the formula, I have 2 to the negative 1. Well, that means I have a fraction with 2 on the bottom, so this is 1/2. This would be 2 to the negative 2, because I have the negative in front of the n value. Okay, 2 squared is 4. The negative exponent means to make it a fraction. This would be 2 to the negative third, or 1/8, and 2 to the negative 4, which is 1/16. So if I wanted to show what my rule is, to get from 1/2 to 1/4, I had to multiply by 1/2. 1/4 to 1/8, I'm multiplying by 1/2. If I wanted to show this by take a number and divide it by the one before it, let's take 1/8 and divide it by 1/4, which is 1/8 times 4/1, which is 1/2. So my first term, a sub 1, is 1/2. My rule is 1/2, multiplying by 1/2. Okay, we could also say dividing by 2, but since we want a ratio, we're going to say this as multiply by 1/2. And if I'm writing a recursive formula, I have a starting value. To get to the next value, I look at the previous value, previous term, and multiply it by 1/2. All right, so this is my recursive rule. Same thing with number 3. Show that the sequence is geometric. So this time I have 4 to the nth power. So here's my 4 terms. This is 4 to the first power, n is 1, so this is 4. 4 to the second power is 16. 4 to the third power is 64, and 4 to the fourth power is 216. So if I'm looking from one number to the next, 4 times 4 is 16, times 4 is 64, times 4 is 216. So my common ratio is 4. My first term is 4, and to get to the next term, I'm going to multiply by 4 to the previous term. So this is my recursive rule. This is the same thing if I did a to the sub n minus 1 times 4. Sometimes it's just neater if you put the coefficient, which is the rule, in front of the n minus 1. All right, so now we're just looking at writing a formula. Okay, so the other side was a recursive rule, but if I wanted to find any term in the sequence, let's say I wanted to find the 11th term or the 33rd term, I could use this formula right here. So this is to find any one specific term. So in example 4, it's asking us to find the nth term of the geometric sequence. So that means that n is just going to stay n. So in this case, I have a first term. I need to know what the rule is. So to get from one number to the next, I need to know what am I multiplying by. So probably easiest to just do the first two numbers. So this is going to be 9 divided by 10. So my rule is to multiply by 9/10. If I did the next one, 81 divided by 10, divide it by 9 means multiply by 1/9. And you can see if I cancel out here, this is going to still be multiply by 9/10. So in part A, I know that my first term is 10. My rule is 9/10. So if I use this term here to find any term, I'm going to take the first term, which is 10. I'm going to multiply it by 9/10, and my exponent would be n minus 1 power. That's how I'm going to find any term in the sequence. Part B says to find the 9th term in this sequence. So here I am going to plug in my formula. I'm going to plug in 9. So I have a sub 9 equals 10 times 9/10 to the 9 minus 1 power. So here I have 9/10 to the 8th power, and then I'm going to multiply that by 10. And that's going to be approximately 4.304. Okay, so you have to do the 9/10 to the power first. That answer you'll multiply by 10. And then part C says to find the recursive formula for this sequence. So in a recursive formula, we have to know the starting value. This is A1. And A1 is 10. And to get to the next term, you're going to multiply, the rule is 9/10 times A sub n minus 1. I didn't have to put the parentheses there, but slip of the pen. So starting at 10 to get to the next term, I'm going to multiply that previous term by 9/10, and that'll get me to 9. Okay. Now we're finding the sum of a geometric sequence. All right, so the sum of the sequence is we're going to take all the numbers and add them all together. And we have a formula here that basically says if I want to add all these numbers up, and here's the summation notation that we did before, we're going to start with the first term, multiply it by the rule to the n minus 1 power. And just by doing some algebra, we actually end up with this formula right here. So on this one, I'm going to write that again up at the top of the page. Oops. A sub 1 times 1 minus r to the n over 1 minus r. So in this formula right here, here's the formula, and they're giving us all these terms, but here I'm going to the nth power. Okay, so it doesn't tell me where to stop. So if I want to find the first number of terms, I don't know when to stop. To find that sum, I'm going to multiply the first term, which is 1/2, times 1 minus r to the n power. And I don't know where I'm stopping, but I do know that r is actually 1/2 to the n power. And then I'm going to divide, not this whole thing. I'm going to write this again. So I have 1/2 times 1 minus 1/2 to the n power over 1 minus, my common ratio is 1/2. All right, so if I do a little calculating here, this part right here, 1 minus 1/2 is 1/2. So if I have 1/2 and then I'm dividing by 1/2, these actually are going to cancel out. And I'm left with 1 minus the rule to the n power. And that will actually work for any number of terms. Now, sometimes when you're adding up numbers, let's take some numbers like 2, 6, 18, 54, on and on and on. And if you can see here, my rule is divide by 3, or sorry, multiply by 3. So when my rule is big, I am going to keep getting big numbers. So if I have a lot of numbers, and this is actually, I'm going to zoom in here. This is actually going from 1 to infinity. These numbers keep getting big. So if they keep getting bigger and bigger and bigger, when I go to add them up, this is going to go to infinity. So actually, I'm getting a little bit ahead of myself. So when a series, and I'm going to zoom back out, I'm talking about diverging here. So if something keeps getting big, towards bigger and bigger and bigger, it's going to infinity, or it can get smaller and smaller. If my numbers here are negative numbers, let's say I started with a -2 and then -6, then -18, I could go to negative infinity, and we call that diverging. It doesn't go to a specific number. It goes to infinity or to negative infinity. But when I'm adding up numbers that are actually getting smaller, like I have up here 1/2, let's say I have 2, and then I have 1/2, then 1/4 times 1/8. And if I'm adding all of these up and I'm going to n is infinity, an infinite number of terms, these are going to approach a specific number. So this is going to get close to a specific number. And that is called converging. So if something converges, it goes towards something. If it diverges, it goes away from something. So this is just going to infinity. Converging is going to a specific number. And we know if something is going to converge or diverge if I look at the rule and the absolute value of the rule is less than 1. So that just means that the rule is going to be between 0 and 1. Okay, so between 0 and 1. And I'm going to show you an example on the other page. And here, I'm going to write this rule up here so I can reference it. That's my formula. So this is my rule. My rule is less than 1, so it's going to converge. Now, to be able to use this formula, I need to know my first term. My first term here is 2. So a sub 1 is 2. I need to know the common ratio. Well, this one's kind of hard to just determine mental math. So let's take one of the numbers. Let's take 8/9 and divide it by 4/3, which is 8/9 times 3/4. And if I were to cancel common factors, this is 2 on top, 3 on bottom. So my rule is, or my common ratio is 2/3. So now if I plug this in here, the sum of all these numbers, and these are just going to, be getting smaller and smaller and smaller fractions. So the sum of all of these numbers would be 2 divided by 1 minus 2/3. And this on the bottom would be 2 divided by 1/3, or 2 times 3 over 1, which is 6. So if I keep adding these numbers that are getting smaller and smaller and smaller and smaller, this sum of these numbers is getting close to 6. Okay. Now, an example of where we could actually see this is that number that we see on our calculator, 0.999999999, and we just call it 1. I'm going to show you using convergence with the summation how that actually happens. So if I know I have 3 over 3, that gives me 1. If I have 1/3, that gives me, on my calculator, 0.33333. That's repeating. I'll put another one in here. But I also know that 1/3 plus 1/3 plus 1/3 is 1 whole. But if I were to add up 0.33333, if I were to add these up, I would get 0.99999. All right. So if I were to use a sequence in a series, I'm going to say a series. Remember, a series is just adding up all the terms in a sequence. So if I were to write this over, I could write this as 0.9 plus 0.09 plus 0.009 plus 0.0009, and I could keep going. But if I have this pattern, this geometric sequence, I start with 0.9, and then to get to the next term, this is I'm going to write this as 9 over 10, and this is 9 over 100. This is 9 in the thousandths position. This is 9 in the 10,000ths position. Now I can see here that I have a common ratio of multiply by 1/10. So if I take 9/10 and multiply it by 1/10, I get 9 over 100. If I multiply this by 1/10, I get 9 over 1,000. So my common ratio is 1/10. So if I were to write the summation where I'm starting with the first term, and let's just go to infinity, because remember, this keeps going on and on and on and on. My first term is 9/10. I'm going to multiply by 1/10 to the k minus 1 power. But if I wanted to find the sum of all these terms together, I can just use this formula. So S equals my first term, a sub 1 is 0.9, over 1 minus my common ratio, which is 1/10. So this is 0.9 on top, and on bottom I have 9/10, which they're the same thing, so I just get 1. So we just showed how all of this, 3 of these, becomes 1, which is what it should be if I'm adding 3/3 together. All right, so that was just a nice quick little proof. All right, so we have practice on these, and then we'll practice for our quiz and take our quiz by the end of the week.